Welcome to this second lecture of 2 on Hamiltonian mechanics in this course. In the last lecture, what we did was build up all the foundations of Hamiltonian mechanics, looking first at Legendre transforms, then doing a Legendre transform of a Lagrangian to get ourselves a Hamiltonian. And right at the end, we looked at how, the Hamiltonian takes a form where you add the kinetic energy to the potential energy, and so it has a really important physical meaning in physics as the total energy of the system. What I want to do in this second lecture, since we didn't do it in the last, was actually solve a real problem using Hamiltonian mechanics so that you can see how that problem solving works. And the problem I'm going to solve is the simple harmonic oscillator problem, partly because you're familiar with it from first year, partly because it's a single variable problem, which means that it's quite easy to do as a start. And in some of the tutorials, you will see 2 variable and multivariable problems. So you'll sort of be able to build from this approach that we show today. And the third reason why I want to do it is because I want to look a little bit at oscillator phase spaces as a prelude to the next lectures in this course, which will be on damped and forced oscillators. Okay, so I want to do a little bit of work here to set ourselves up for the next coming lectures. And then in the second half of this lecture, what we're going to do is step back from problems and be a little bit more algebraic again. And we're going to look at an important concept that comes up in Hamiltonian mechanics, which is the Poisson bracket. And the reason why this often comes up, and it's a good point for it to come up, is that it's the thing that connects from Hamiltonian mechanics in classical mechanics to the concepts of Hamiltonians and time dependence on Hamiltonians in quantum mechanics. And what we'll see is that the Poisson bracket has an analog in quantum mechanics, which is the commutator bracket, which if you've done both of these courses, you'll see the parallels between the two. Okay, so that's where we'll finish with Hamiltonian mechanics for this course, aside from solving lots of problems with it. And in the coming lectures, we'll switch topics to oscillators for a little while. So let me bring up some slides. The problem we're going to deal with today is one that you'll be very familiar with from first year, which is the simple harmonic oscillator problem. So what we have here is a flat surface. We can either have a block that's sitting on a frictionless surface and able to slide backwards and forwards, or if you want to make it a little more realistic, you can have a mass on some frictionless wheels that can slide backwards and forwards. It's connected to a spring, by a spring to a wall here. The spring has spring constant K, the cart has mass M, and it has some position X away from the equilibrium position. The equilibrium position is the point where if you put it, there's no force subjected on it by the spring, okay? So let's kick off with this problem. I'm going to need some paper. And I always find when I do problems, it's kind of useful to just start by resketching the problem in a really simple form. I always find this good in exams as well, just to make sure that the examiner knows that you're on the same page as they are with the problem and you kind of understand how the problem goes together, particularly if it's kind of problem where it's described in words and doesn't already have a figure to it. So here's what we'd have. Simple mass sitting on a surface connected to a wall by a spring, and it's some distance x away from the equilibrium position. We've all dealt with this sort of problem before. If we wanted to, what we could do here is just start with the Hamiltonian and say that it's going to be the kinetic energy plus the potential energy and come out with a form for our Hamiltonian. But since this is kind of new, what I'm going to do is use this as another example of doing a Legendre transform to get from the Lagrangian to the Hamiltonian because it's nice and quick to do, okay? So let's start out by getting the Lagrangian for this system. Which is going to be the kinetic energy minus the potential energy. Okay, so we can write some expressions for these things up here. So the kinetic energy for this system T is going to be a half mx dot squared. As we know, it's x dot is the velocity. It's half mv squared, and the potential energy in here is going to be a half k x squared. You should all be familiar with the potential energy for a spring from first year, but just to connect it back to the force, the force is equal to minus du on dx in this case. So this will be minus, the 2 will drop down and cancel out the half, so we'll have minus kx. And so our force is just a restoring force minus kx pointing back towards equilibrium position. Okay, so the potential energy makes sense. We can now calculate our Lagrangian. It's pretty simple. It's a half mx dot squared. Put the dot in the right place. So we would have minus a half kx squared just in here. Okay. All right. So as you remember, the first step to doing our Legendre transform is to define our new variable. And our new variable in this case will be the thing that we call the canonical momentum, right? So our canonical momentum P, and we don't need an I here because we're dealing with just one variable X, so there's only going to be one P connected to it. It's going to be dl on dqi dot, and in this case qi will be x, so it'll be dx dot, right? Dx dot just here. And so if we take the derivative of our Lagrangian, which is on the line above, with respect to x dot, the 2 is going to drop down to cancel out the half, and so we'll have mx dot here, and the potential energy term on the end will contribute no terms in x dot, so it disappears. Okay, so what we get here is pretty much what we expect. The momentum P is equal to mx dot, or mass times velocity. Fairly simple, straightforward thing in here. Okay, mostly because we're dealing with one coordinate and it's a translational variable, so it behaves itself quite nicely. So now we can do our Legendre transform to get our Hamiltonian, and it will be from I equals 1 to n of pi qi dot minus L. And of course, we only have one variable here. So this thing is going to be px dot minus L, okay? So we can now go through and work this thing out. Our momentum above, we've already calculated it, it's mx dot, multiplied by x dot, minus our Lagrangian, which we had just above. So this is a half mx dot squared minus a half kx squared, like so, okay? So this is going to be mx dot squared minus a half mx dot squared plus a half kx squared in here. And this first term resolves to a half mx dot squared plus a half kx squared. And if we have a look back up the top here, you'll notice that this thing is just the potential energy plus the kinetic energy plus the potential energy. Okay, it's total energy of the system. So if we really wanted to here, we could have just cut directly to the chase and just gone h is equal to t plus u, which is a half mx dot squared plus a half kx squared. But I did the Legendre transform just to demonstrate again that this thing all fits together, and that the minus sign that you see in the Lagrangian turns into a plus sign that you see in the Hamiltonian when it's associated with a potential term switching between the two. Okay. All right. So the next step in here, if we were doing a Lagrangian problem, what we would do is take the two derivatives. So derivative of L with respect to Q and derivative of L with respect to Q dot. And then what we would do is put those two things into the Euler-Lagrange equation. We'd be taking the time derivative of the Q dot derivative there to get us one equation of motion in this particular case. The Hamiltonian version of this is nicer because when you get the derivatives that you need with respect to the Hamiltonian, there's two of them, those already give you the two Hamilton's equations. So this pops out pretty quickly, right? So what we're going to do here is get Hamilton's equations. And we have them from earlier. They are pi dot is equal to minus dh on dqi. And qi dot is equal to dh on dpi. Okay, like so. All right, so now we really just have to take two derivatives here. And we're only dealing with one variable. So we can write this pretty quickly as P dot is equal to minus dH on dx. And if we take our Hamiltonian and take the derivative with respect to x, 2 drops down and kills the half, which gives us a kx, and the x dot term drops out. So this thing ends up being minus kx. Okay, so the kx comes out positive from the Hamiltonian and the derivative. We put a minus sign in front of it, we get minus kx. The time derivative of the momentum, of course, is the force, right? So what this is really saying here is that the force is equal to minus kx. And that, of course, is what we know because we calculated that right up at the top, okay? So this first Hamilton's equation really is just telling you what the force is in this particular problem. The second one, qi dot is now going to be x dot, and it's going to be equal to dH on dP. And the important thing in here is that we now need to write the Hamiltonian that we had earlier in terms of P rather than x dot, okay? Now, we know that our mx up there is equal to P. So let's just clean up the Hamiltonian for a second. Our Hamiltonian is going to be equal to a half mx dot squared plus a half kx squared. And of course, this is 1 on 2m mx dot squared plus a half kx squared. And so this thing really is just p over 2m, p squared over 2m plus 1 over 2 kx squared, okay? So we've now got our Hamiltonian written in terms of our two variables that we use in the Hamiltonian form, the momentum p and the position x. Okay, so this is a really good habit to get into when you're solving these problems. And I left it a little bit just to highlight the fact that you need to do this. When you write your Hamiltonian, what you want to do is try to get it in terms of momenta and positions, because that makes it easier to work with. When you're dealing with your Lagrangian, you try to want to write that in terms of positions and velocities, because that makes that easier to work with, right? So for Lagrangians, Q's and Q dots. For Hamiltonians, try to write it in terms of Q's and P's, because if you do, then it's a lot easier to work with, okay? All right, so now we can step back up here. If we take the derivative of our Hamiltonian with respect to P now, 2 will drop down and knock out the 2. And so what we will get in here is P over M, and we're dealing with a translational variable here, so we know that this thing really is just the velocity, right? And of course it's x dot, it's just the velocity, all right? So the thing that you'll see here pretty much straight up, at least in this case, which is a translational problem, is that your two Hamilton's equations will pop you out P dot, which will be the momentum, and your Q dot, which in this particular case will be a velocity, okay? All right, the problem that we have here is analytically solvable, so we can do it, right? And the thing that you're usually looking for in any mechanics problem is to get at the forces or to get at the accelerations, okay? So what we want to do is to get at x double dot in this particular problem. And we already have x dot. So what we can do is take x dot and differentiate with respect to time. So let's go to equations of motion here. Our x double dot will be equal to d on dt of x dot, which will be d on dt of p over m, just using our expression that we got just up here for our x dot. And of course, the mass is not going to be changing with time here, so the only thing that's differentiable here with respect to time is the momentum, right? So what we're going to get in here is p dot over m, and fortunately, our other Hamilton's equation has given us our p dot. So this is going to now be minus kx over m. The thing that you will know in here is that for simple harmonic motion, hopefully you've seen this in first year, omega is equal to square root k over m. And so k over m is going to be equal to omega squared. And so we can basically just write this thing as minus omega squared x. And that's our usual equation of motion for simple harmonic motion, right? X double dot is equal to minus omega squared x. You can go through and solve this. You'll have all done it in your first year courses, so I'm not going to labor the point by doing it here, but you will end up with something that looks like this. X of t is equal to a cos omega t minus phi, where phi is just a phase factor, which tells you where you start in phase at a particular point in time. And your momentum in here would just be mx dot, for example. And if you take the derivative of your x just above, so this will be minus ma. When you take the derivative, you'll get an omega popping out from the cos. When you take the derivative of cos, you get a minus sign, which is why I've already written the minus sign there, sine omega t minus phi, just in here. Okay, so there's the position, there's the momentum. We've solved the problem. We've just done it with Hamilton's equations, and it pops out fairly quickly out of the problem, as you would expect. So sure enough, we get the usual behavior that we'd expect for simple harmonic motion in a problem. And I'll let you play around with other problems to build this up into bigger Hamiltonian problems as other parts of the course. The one thing I want to pick up just before I finish in this half of the lecture is you'll remember last time we talked about phase space, and we're now in a really nice position here where we can actually draw a phase-based trajectory for this particular example. So we now have a phase space. It's going to be a two-dimensional space because there's two coordinates here. One is going to be the position x, the other one is going to be the momentum p. We can draw these on two axes, like you can see here, p and x. And then we can draw the equation for our system in two particular states here. One is the oscillator released from rest at an initial position A. So we would be starting right over here and then just let the system go and look at how it moves through this phase space. And the second one is the oscillator initially at x equals 0 and released already with some momentum. So what we'd do is start at 0 and just go thunk, and it will just move off and start doing its oscillation. Okay, and so that would be this position here. We're at position x equals 0 with some momentum, and it will kick off. Okay, whereas in the first case, we're at some position x, which is equal to a, and momentum equal to 0 because we're on this momentum axis. Okay. What happens with phase spaces is essentially you've got the coordinates describing the motion of the particle, and they will evolve as a continuous trajectory as a function of time. Okay, so what we're plotting here is basically how the momentum and position of this particular system evolve as a function of time. And so let's consider the first case here. You have your mass on the spring, you'll pull it away to some amplitude A and hold it at rest, and then you'll just let it go. And what'll happen when you let it go is it will start being pulled by the spring back towards the equilibrium position. So x will start to get smaller, p will start to get larger. Both of the p will be negative because it'll be trying to drive it in the negative x direction. The x will go from a towards minus a. And so this is exactly what you see here. This starts to move along this trajectory in phase space. So it's basically a line. It will get to the point here where it has x equals 0, so it's at its equilibrium position. It has its maximum negative momentum, so it's traveling at its fastest at that point. it will move through that point, travel out towards where minus A is. When it gets to minus A, it actually stops, okay? And then begins to turn around and be pulled or pushed by the string. You know, if we imagine our setup as the cart, we pulled it out, let it go. It goes back through the equilibrium position, compresses the spring starts to push it back out again. Okay, so when it gets to minus A, it's got no momentum, which is why you're sitting on this axis here, and then it will start to accelerate back towards the equilibrium position. So now we start moving back towards positive X with positive momentum. Okay, so positive momentum is driving it towards the right. We'll go through, you'll hit the equilibrium position just in the middle. That's when you've got your maximum momentum. It will head out towards the positive amplitude again and end up here. And as you can see here, this trajectory is actually is an ellipse. So it will go round and round and round this thing, which corresponds to starting at it where the amplitude is, moving through the equilibrium position to the minus A position, back through equilibrium to plus A, and boom, doom, 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 is just going round and round and round and round this phase space, okay? This other position here on the inside is you start at equilibrium and you give it a kick with positive momentum, so it will move out to the amplitude, maximum amplitude, which is out here, move back through the equilibrium position again with the opposite momentum that it had when we kicked it off, head to the negative amplitude, and then head back out, and so it will do the same thing, okay? What you'll notice is that this circle will stay constant all the time. And the circle case stays constant all the time because all you're basically doing is conserving the total energy of the system. And what you're doing is converting it from kinetic, entirely being kinetic energy, which is when it's traveling through the equilibrium position with its maximum positive or maximum negative momentum, through to being entirely potential energy when it's at the two amplitude points. Okay, those are the points where it's becomes stationary, so it's got no kinetic energy, and all of its energy is stored as potential energy. And so as it moves through this cycle, what you basically have is kinetic energy being converted to potential energy, being converted to kinetic energy, being converted to potential energy, and around and around and around and around it goes. And in the ideal case of simple harmonic motion, where the energy is conserved by that system forever, you'll just run around this trajectory again and again and again and again. Okay, and what we'll see in the coming 2 lectures is that if you put damping in other words, you let the system lose energy, or you put forcing in which case you start to add energy to your oscillating system, then these trajectories will either spiral inwards or spiral outwards, or you can, or so forth, okay? This is probably a first good example, at least in this year's course, of what phase spaces really look like. They're really just mapping the dynamics of the system graphically into a space that tells you what all of the relevant dynamical coordinates for the system are. And they're useful for really simple systems like this, just to try and visualize what's going on. But if you go on and do a subject like chaos and dynamical systems, what you'll find is that these become absolutely essential to understanding what's going on with the system. And there, in a lot of these bigger dynamical systems, you're actually dealing with multi-dimensional spaces. So what you often end up doing is taking slices through them to try and reduce the number of coordinates. So you'll end up seeing 2D plots that will be sections of this larger multi-dimensional space that relate to what the dynamics of the system are. Okay. There's 2 notable aspects of trajectories in phase space that I'll just point out now, and you'll learn more about this if you go on to do a course on chaos and dynamical systems, because we don't really have enough time in this course to go into that as much as I'd love to, because it's actually a really cool topic. So there's 2 points here. One is if H is explicitly independent of time, then the different phase space trajectories cannot cross the same phase space point ever. And if they do, they're just the same trajectory. Okay, you can see this in the in what's going in here, right? This trajectory for the smaller oscillation will never cross this trajectory that you have for the larger oscillation. They will always be sets of ellipses that run outwards and if H has no explicit dependence on time, as we saw in the last lecture, that means the energy is conserved, and so it can't change its size, and so these things will never cross. Okay, so what we're really finding here is that if your system conserves energy, in other words, it has no explicit time dependence for the Hamiltonian, then phase-based trajectories just can't cross the same phase point ever. Okay, and I've just put the little Ghostbusters thing in here because this is always the way to remember it when you get into dynamical systems. Phase-based trajectories just never cross the phase-based trajectories. Bad things happen if you do it. This breaks down a little bit if you have a Hamiltonian that has an explicit time dependence. In other words, the energy of the system is not conserved. It either loses it or it gains it, or as a function of time, it might even gain it and lose it and do a few different things. In that case, the different phase space trajectories can't cross a phase space point at the same time. If they do, then they're the same trajectory. Okay, so you can imagine having our two oscillators on the previous page, and if they were bleeding energy, so losing energy as they oscillated, the inner one would spiral inwards towards the center, and the outer one would gradually spiral inwards towards the center, right? You can imagine this if you take a spring, if you let it lose energy, it will come out a little bit less each time, so its amplitude will get smaller, and the amount of momentum it has when it crosses through the equilibrium point will get smaller as well, okay? And the important thing here is if you start those two problems, those two trajectories at the same time, they will work their way in, and they will never end up at the same place at the same point. They will spiral in, and the one spiraling in from the inside, the outside one will also cross it at some point because it will spiral into 0 too, but they will never cross the same point at the same time, okay? Otherwise, they basically would have been the same trajectory. I'll leave the deeper aspects of that for dynamical systems courses where you'll see, nice complicated phase space trajectories like the strange attractor that you see for chaotic systems, and pretty much leave it there. The main thing I wanted to do was just introduce this idea of phase spaces, particularly with respect to oscillators, for the next two lectures, since we're going to look at it a little bit. That's the end of this first half, so let's take a short break, and on the other side, what I'm going to do is deal with Poisson brackets.